Hello everyone, welcome to lecture on microprocessor systems and interfacing. My name is Dr. Vilayat Khan. I'm an assistant professor at Comsets University, Islamabad, WA campus. These lectures have been edited from these two sources. The topics of this lecture are instruction set of Intel family of microprocessors, in particular 8086 microprocessor, and some data transfer instructions in the instruction set of microprocessors. To understand what are instruction set, we first need to understand what is a program, a computer program. A computer program is a set of instructions written to solve a particular problem. We need to solve a particular problem. For example, we need to call a person, then we need a program or an application to do that. Or if we need to add a few numbers, two numbers for example, then we need an adder program to add two numbers, and for that we need a computer program to solve addition problem for us, for example. Then each program is a set of instructions. A program may consist of just few instructions, or it can consist of millions of instructions or thousands of instructions. So a set of instructions then form a program. Then an instruction is just simply guides the microprocessor to do or to execute a task or a part of task. So instruction are directions which a microprocessor needs to follow to execute a task or a part of task. So each program consists of a number of instructions, and each instruction just execute or solves a small problem, and all these problems together form a big problem or an application. To write instructions to create a computer program, instructions are written using certain rules, and those rules are defined by the programming language. So each programming language defines a set of rules to write instructions for creating computer programs. So just like natural languages, where certain grammar is followed to write sentences, and then multiple sentences together form an essay. Just like that, computer programs are also written using certain rules or grammar defined by a programming language. So to write programs, there are two levels of computer programming languages. One is called high-level language, and the other is called low-level language. The high-level language is more user-friendly and is quite similar to the natural languages, where English letters or English words are used, and they're quite easy for the user or for the programmer to understand, and also to write programs in the high-level languages. For example, Java, C++, these are high-level languages. But on the other hand, they're quite difficult for the computer machine to understand. They cannot be directly interpreted by the computer machines. On the other hand, there is another group of languages called low-level languages. As low-level languages are quite close to the computer machines, and machine can understand them easily, but they're difficult for the human beings to write programs in the low-level language and also to understand them, because they are quite far from the natural languages as compared to the high-level languages. There are other group of two. There are two other forms of languages in the low-level languages. One is machine language, and the other is assembly language. Machine language, as the name represent, is a sequence of bits and is the language that is easily understood by the computer machine. So in machine language, instructions that make the program are just a sequence of binary bits, and these binary bits are then fed to computer microprocessor hardware, which the microprocessor hardware can interpret and perform a certain task. And then all these tasks together form a bigger problem, and which is being solved, and we call all the setup, those instructions written in the machine language, a program. Okay, so as compared to machine language, the assembly language is comparatively easy for the programmers to understand and write programs, and because they are using English alphabets, mnemonics, and then these English alphabets or mnemonics are then translated or interpreted to binary sequences of the machine language using a program called assembler. So assembler is basically a compiler that translates instructions or code written in the English mnemonics or English alphabets to a sequence of binary bits in the machine language. So user programmer has to write initially complicated or very complex applications using high-level language. Then compilers are used to translate those programs from the high-level language to assembly language, and then assemblers are used to translate the code in assembly language to machine language. So certain levels of translators or compilers are used to facilitate or to automate this process of creating or generating machine language code. Okay, so each instruction in the program operates on certain data, and there are those the data is stored in either memory in some location in memory, or the data is stored in registers inside the microprocessor. So each instruction programmer can define different ways how to reach the data to be operated on by that specific instruction. So the different ways in which a source or destination operand or data is denoted in an instruction are known as addressing modes. So for example, this is a move instruction. This is an assembly language instruction which is using English alphabets to write instructions. So this MOV are the first three letters of English word movement or move. So it moves the data from one location to the other. So in this instruction, we have two operands. One is the source of operand. One is source operand, and that is the name of the register BX. BX is the name of the register from where the 16-bit data is being moved to the destination, where the destination is a register. So, and this instruction moves 16-bit data from the BX register to a destination or AX register. And in this instruction, there are two operands, and each of the operand can change. Their addressing mode can change, and based on the ways where the operands or the address of operands is defined, define different addressing modes. Okay, so microprocessors supports 6 types of instructions. These 6 type of instructions are given here. Data transfer instructions. These instructions are responsible to transfer data from one location to the other. and there is another group of instructions called arithmetic instructions. These instructions are responsible to perform arithmetic operations on data. For example, adding two values, subtracting, multiplication, and division. Then there is a third group of instructions called logical instructions. Logical instructions are responsible for logic operations, for example, comparing two values, if one is less than the other, or if one is greater than the other, or if the two values are equal. So logical operations are performed by logical instructions. Then there is a fourth group, string manipulation instructions. These instructions are responsible to manipulate string data, for example, to move string data from one location to the other. And then there are process control instructions. These instructions control system processes. And then there are control transfer instructions. These instructions are responsible to transfer control from one programming location to the other. These group of instructions are discussed one by one in coming lectures, but the main focus of this lecture is on data transfer instructions. Data transfer instructions are instructions that are used to transfer data address or in register or memory locations and input and output ports. So these instructions are used to transfer data, or it can be address, into registers inside the microprocessor, or into the memory locations, or into the input and output ports. Or the transfer can be from these, can be from the registers, can be from the memory location, or it can be from an input and output port. Generally, these instructions involve two operands. One operand defines the source of the data, and the other operand is normally the destination for the same data. For example, in the previous slide, move instruction was transferring data from one register to the other. So one register was the source of the data, and the other register was the destination of the data. Source register, it can be a register, it can be a memory location, or it can be an immediate data. Immediate data is the data which is not stored, which is not accessed separately from the register or from the memory location, but it is part of the instruction. So it is stored along with the instruction. So the source of data can be the register, can be the memory location, or it can be provided as part of the instruction. While on the other hand, the destination of data can be a register, or it can be a memory location, but it cannot be an immediate data. The size of data should be either a byte or a word if we are talking about the 8086 microprocessor, but it can be longer. The size of the data can be longer if we are using other microprocessor, for example 80286 or above microprocessor. The data can be 32-bit. So in 8086 microprocessor, an 8-bit data can only be moved to an 8-bit register memory, and a 16-bit data can be moved to 16-bit register memory. The same rules applies to other microprocessors as well, but in 8086 only 8-bit data or 16-bit data can be moved, because the sizes of registers, the maximum size of the registers is 16-bit. An 8-bit data can only be moved to 8-bit register or memory location. If an 8-bit data is moved to a smaller memory location, which is normally each location is at least 1 byte. But if, for example, if a 16-bit data from one register is moved to an 8-bit register, for example, or an 8-bit memory location, then this is not allowed. This is an overflow condition. Okay, so in each instruction, when the data is being operated on by the instruction, then the data is to be accessed from the register or from the memory location. If the data is accessed from the memory location, then certain registers and addresses are used. The physical address of the memory location, or just the memory address, is calculated using segment address and an offset address, which is provided by another register. So, for example, this is the programming model of the 8086 microprocessor. This part is the bus interface unit. There are some registers responsible for providing the starting address. For example, the segment registers would provide the starting address of the segment, and there are some registers in the execution unit. So this part is responsible to fetch an instruction from the memory inside the microprocessor, and these registers are mainly responsible to execute that instruction. In this unit, there are registers, accumulator, base count, data, and there are some other registers: stack pointer, base pointer, destination index, source index, and there is a flag register. While in the bus interface unit, there are some segment registers. To calculate memory address for the data to be accessed from the memory, the memory address calculation process begins with the segment register. So whatever the memory segment is being accessed, the corresponding segment register is accessed first, and a 16-bit value is taken from that segment register. Along with that 16-bit segment register, 4 zeros in the binary are appended at the right side to make that 16-bit value a 20-bit value. So this is a 16-bit register content taken from the segment register, and then this 16-bit value is left shifted by 1 hexadecimal digit, or by appending a 0 on the right hand side, or by appending 4 zeros in the binary system. So this is equivalent to appending 4 zeros or in the binary, or appending a single 0 in the hexadecimal, or by left shifting the 16-bit content from the segment register. So at the end, we get a 20-bit value here. So we get the 16-bit value from the segment register. We left shift that value by 1 hexadecimal digit, or by 4 binary digits to the left. And so at the end, we get 20-bit value. And then an offset, 16-bit offset value taken from another register is added with this 20-bit value. An adder is used to add the 16-bit offset value and this 20-bit starting address of the segment. So this 20-bit address is actually the starting address of the memory segment. But where in that segment to access this 16-bit offset value is added with this 20-bit value, and at the end, the physical address, or the memory 20-bit memory address, is calculated or computed. And then this 20-bit memory address is then used by the microprocessor to access data from that memory location. Okay, so now we are clear how the memory address is calculated when assembly language instructions are executed. So data transfer instructions, there are a number of data transfer instructions, but in this lecture only a few of the data transfer instructions will be discussed. MOV and XCHG instructions transfer data from one location to the other. So if we are using MOV instruction, then in general there is an opcode of the instruction MOV, and then there is a space, and then there are two operands. The first operand is the destination of data, and that destination can be a register or it can be a memory location, while the source of the data can be a register and it can be a memory location. But remember that the source and destination cannot be memory at the same time. So a memory location here is the destination, and a memory location here is the source is not allowed. So only memory can be either a source or it can be a destination. But if both the source and destination are registered, then this is allowed. So this format would give us these three types of MOV instruction. For example, in the first type, MOV is the opcode, space, then there is a register, and then there is another register. So the source of the data is a register 1, and the destination of the register the data is also a register 2. So source and destination both are registers, microprocessor registers. So this instruction would move content from this register 1 to this register 2. So this register 1 and register 2 are microprocessor registers. Depending on the microprocessor, there are a number of registers, and their sizes can vary. For example, in the 8086 microprocessor, registers are 16-bit registers. For example, this move AX, BX is an instruction that moves 16-bit content from this BX register to AX register. So both of the source and operands, source and destination operands are registered in this instruction. So this is specifically an instruction addressing mode used in this instruction, and that addressing mode is the register addressing mode, because both of the source and destination are registers. Similarly, in this category, there is another form of move instruction where the destination is a memory location while the source of the data is a register. So this instruction would move content from register 1 to a memory location. And this memory location can be defined by different ways, using different memory addressing modes. For example, there is a move instruction where 1, 2, 3, 4, there is an H missing, which means hexadecimal. And the bracket means that this value is not data, but it is an address. An offset address is provided here. So this instruction would move 16-bit content from this BX register to a memory location in the data segment defined by this offset address. So the offset address 1234H is added with the value from the data segment, left shifted value from the data segment register, and a physical address or memory address is calculated. And the 16-bit value is stored on that location plus next higher location. Similarly, in this addressing mode, where the memory source is the memory location and the destination is the register, it is just the other way around of this form of move instruction. So the source is a memory location, the data is moved from a memory location defined here to a register 2 in this case. And this is an example of this addressing move instruction form, where 1234H is a hexadecimal value, a 16-bit offset address. So these brackets again indicate that this value is actually an address and it is not a value. It is not a data. So microprocessor would generate a memory address or physical address by left shifting the content, 16-bit content of the data segment register, and then adding this offset value, and a physical address would be calculated. And then 2 bytes of data from that memory location are transferred to this 16-bit register. Then there is another group of move instructions in this form, where the destination is either a register or it is either a memory location, while the data is while the source of the data is an immediate data. So this data is not stored in a register and it is not stored in a memory location, but it is stored as part of this move instruction. Then there are 2 forms in this group, MOV space, then there is a register, and then there is a data. So the immediate data in this case is moved to a register. For example, we have an instruction MOV BX, 1234H. Remember, we are not using brackets as we used here. So this 1234H is now a data and it is not an address, because brackets are not used. So brackets are very important in these assembly instruction. So what happens here is the 1234H 16-bit data is moved to this BX register. And then there is the other form of instruction where the immediate data is moved or stored at the memory location, unlike the register which was used here. So the data is transferred or moved to the memory location. So here 1234H is the data, immediate data, and this immediate data is stored at the memory location of the data segment addressed by this address. So what happens that a microprocessor first calculates the physical address of the memory destination where this data is to be stored. So a microprocessor address calculation begins with taking 16-bit value from the data segment, shifted by one hexadecimal digit, and then this offset value is added with that 20-bit value, and a 20-bit physical address or memory address is calculated. So this 1234H is 16-bit value is stored on that memory location. And this category we have exchange instruction. So exchange instruction exchanges data between these two operands. The source can be a register and the destination can be either a register or it can be a memory location. So this instruction exchanges the data between these two operands. So the data from this register is moved to this register 2 or this memory location, and the data from this register or memory location is moved to this register 1. There are two categories, two types of instruction in this group. First is exchange register 2, register 1. In this form of instruction, only a register addressing mode is used. The source operand is register 1, the destination operand is register 2. So the data from register 1 is moved to register 2, and the data from register 2 is moved to register 1. For example, exchange BX. So what happens that the content after the execution of this instruction, the content which was stored before in the X is moved to BX, and the content of BX is now stored in the AX register. Another form of this instruction is that one operand or one argument of this exchange instruction is the memory location. So the content from this register 1 is stored in this memory location, while the previous content of this memory location is stored in the register 1. An example of this form of instruction is here, where 1234H represent a memory location. So the content, 16-bit content from the AX register is moved to data segment memory location addressed by this offset address, and the 16-bit value from the previous 16-bit value from the data segment location addressed by this offset value, this offset address is moved to the AX register. So the content between these two locations are exchanged with each other. The addressing modes used in these forms of move and exchange instruction are register addressing mode, immediate addressing mode, and direct addressing mode. For example, in this instruction, both of the source and destination are registers, so only register addressing mode is used. In this addressing mode, the immediate data is moved to a register, so immediate addressing mode is used. While in other instructions where the memory is being accessed, in those instruction and all of these instruction where the memory was accessed, direct addressing mode was used because the offset address was provided directly as part of the instruction. Here the offset address is part of the instruction. Here the address is offset address is part of the instruction, and here the offset address that is provided is part of the instruction. So this is the memory addressing modes used here are the direct addressing mode. So in all of these instructions, only 3 memory addressing modes are used: register, immediate, and direct addressing mode. If we can introduce other addressing modes in these instructions as well, they're very easy. For example, to introduce register indirect addressing mode, the offset address that was previously provided by directly putting the address as part of the instruction is now provided through the register. So that offset address is first stored in a register, and then that register is enclosed in brackets. So this instruction, for example, would move a 16-bit value in the BX register to the data segment memory location addressed by the offset address stored in AX register. So the offset address is provided again, but indirectly through a register, and that's why this addressing mode is called register indirect addressing mode, because the offset address is provided indirectly through a register. And the same addressing mode is used here because the memory is being accessed, and this instruction would move this immediate value 1234H 16-bit immediate value to a memory location in the data segment addressed by the offset address stored in this AX register. If we remove these brackets, then this addressing mode would become immediate addressing mode, because the immediate value is stored in the register and not in the memory location. And quite similarly, here we have the register indirect addressing mode, where the 16-bit content is exchanged with the memory location addressed by the offset address stored in the BX register. And apart from the direct addressing mode and register indirect addressing mode, other addressing modes can also be introduced in these instructions. This is based addressing modes, register, immediate, and based addressing mode. So the memory addressing mode is changed to based addressing mode, where a base register is used, plus a displacement value is also added with the content in the base register. So what happens here, that the 16-bit content is moved to a memory location in the data segment addressed by the offset address taken from the base register plus this displacement value. So these two values would give us an offset address. So the 16-bit value from the BX and this 8-bit displacement, which is sign extended to a 16-bit value and is added to the 16-bit value in the BX register, would give us a 16-bit displacement on a 16-bit offset value. And this 16-bit value offset value is then added to the 20-bit starting address of the segment, as we calculated for the previous instructions. So this is a based addressing mode, and the same based addressing mode is introduced here, where the offset 16-bit offset address is calculated by adding the 16-bit value in this BX register plus this 8-bit displacement. And remember that this 8-bit displacement is always sign extended to 16-bit value, and then it is added with the 16-bit content in the BX register. Together, this addition would give us a 16-bit offset address, which is then added with the 20-bit starting address of the segment. And the same addressing mode is introduced here and here as well. So the memory addressing modes in these instructions are changed to based addressing modes. And if we continue this way, indexed addressing mode can also be introduced, and that is very simple. Just an index register is introduced. That index register can be a source index register, it can be a destination index register, but in these examples, source index register is used. So what happens that an 8-bit displacement plus an index register are used to provide the offset address for the memory address. So this instruction would move a 16-bit value in the CX register to a memory location in the data segment in the addressed by the offset address calculated by adding the 16-bit value in the source index register plus an 8-bit displacement. And the same addressing mode is again introduced in other memory addressing modes as well, here and here and here. So what happens here, that the 16-bit value in the X register is exchanged with the 16-bit value in the data segment memory location addressed by this offset address. So here we calculate the offset address by adding the 16-bit content in the source index register plus as an 8-bit displacement value, which is sign extended to a 16-bit value, and then add it with the 16-bit content from the source index register. Another memory addressing mode, base plus index addressing mode, as the name specifies, as the name indicates, in this addressing mode, to calculate the memory address, a base register and an index register and a displacement are used to calculate the offset address for this memory address calculation. For example, here the 16-bit value is moved to the data segment memory location addressed by BX plus SI plus 8-bit displacement. So what happens here, that the offset address is calculated by first sign extending this 8-bit displacement to a 16-bit value. This is added with the 16-bit value in the source index register, and this is added with the 16-bit content in the base register BX, and this addition would give us a 16-bit offset address, and which is added with the starting segment address, and a physical address is calculated as usual. So in the other instructions as well, base plus index addressing mode is introduced by using an index register. For example, it can be a destination index register, it can be a source index register, and the base register is also used here. So these three values in these two register plus an 8-bit displacement are added, and an offset address is calculated, which is as usual added with the starting address of the segment to calculate the 20-bit memory address or the 20-bit physical address to access that particular memory locations. So these are different addressing modes in the move instruction and exchange instructions, and of course there are other forms of move instructions. There are other variations of move and exchange instructions. For further detail, I would refer to the textbook of microprocessor, and if there are queries or questions while watching this video lecture, please keep a note of those queries and lectures, and you can ask them during the online session.